All right. So this is just going to be more or less more examples, but let's recap last time what we covered. So we were doing simple circuits, where here we have a battery and a resistor. In this case, they are hooked up in series, which really just means that there's only one path for the current to go. There's only one route for the current to take. And once a steady current is established, there is the same current kind of everywhere in this loop. And the general problem-solving strategy is to first guess a direction for the current everywhere. So let's do the problem down here. We of course can use our physics intuition in that the battery is going to push current in this general direction. And since there's only one battery and there's only one loop, it's going to be a pretty good guess as to what the direction of the current's going to be. But you can draw it either way. And similarly, you can draw a loop to apply the loop rule, and it has to be a closed loop. And I would say the easiest thing on you is to also make it go in the same direction as the current if you can. But for sake of example, let's have it go the other way with this one. So I'm going to draw my loop counterclockwise where the current is going clockwise. And the rules that we apply are that if the loop moves from the negative to the positive terminal, you're going up in potential, you add potential, else you subtract. And if the loop moves through the resistor in the direction of the current, you go from high to low potential, you subtract the potential. So for the battery, it only depends on the direction of the loop. For the resistor, it depends on if your loop is parallel or anti-parallel to the current. So in this case, again, if I start, let's start up here. If I go down through the battery, but I'm going from positive to negative instead. So I'm going from higher potential to lower potential. So then I'm going to subtract the battery. And then I'm going to go to the right through the resistor. But notice that is anti-parallel to the direction of the current. My loop is going this way, my current is going this way. So since they are anti-parallel, I do not subtract, but I add. And then I go up and back to where I started. So then by the loop rule, I set that equal to 0. And then, as a result, we get that the current is the voltage of the battery divided by the resistance. If it's 10 volts and 5 ohms, that's then going to be 2 amps. Since this is positive, so that means our guess was correct. Our guess for the current, for the current direction was good. Again, if we had guessed incorrectly, then it would just have had a minus sign. Okay. So let's see. Anything else we need to do? Nope, that's a simple example. You could try it again. You could try it on your own. There's the battery. There's the resistor again. But maybe your educated guess is that the current goes that way. And then the loop, maybe then you have the loop go this way. Let's just do it. So in this case, then, if I start here, does it matter where I start? No, because I'm doing a loop. So if I start here and I go up, I'm going through the battery, negative to positive. So then that's going to be plus VB. And then as I go over and then down and then left through the resistor, but then notice I'm again going in the opposite direction of the current. So then I don't subtract, but I add plus IR equals 0. And notice that you get I of negative 2 amps in this case, which just means you reverse the direction of I. to commit to the right answer. All right, simple enough. So things that we were able to write down, essentially I is steady. Which you can think of as a constant, not changing. It's not getting used up also, right? It's the same everywhere. Which is a big misconception. I think a lot of people end up thinking that current or charge gets used up. That is incorrect. Charge and current are not used up. The current is the same everywhere in the circuit. In this case, 2 amps everywhere. Now the energy all those charges are carrying around, think of them putting little energy pellets in their backpacks. Some of those backpacks are getting emptied as they go through the resistor, but they still march at a constant rate. Again, because if they, suppose they didn't. Do I have a drawing here? Yeah, let's just draw it up here. Move this up. Suppose it wasn't steady, in that the current was slower once you went through the resistor. So if you had something like this, and the current was slower on the other end of the resistor, then that means charges would be marching along pretty fast out of the battery. But then they would go through the battery, and then they would be slower here. So as a result, and then they would speed back up again when they go through the battery. Essentially, there would be a buildup. So that if I slowed through R, essentially charge would build up. If you imagine that there's a bunch of charge building up here, that's not going to want any more additional charge to go through the resistor and join them. So they're going to start pushing backwards in the other direction, which in fact is going to then just slow down the current everywhere else until it reaches some sort of steady state again. And then similarly, if you could imagine that if it were speeding up at some place arbitrarily, there'd be a void. So current or charge is not used up, energy is, which is essentially, again, the statement of what delta V over a loop is 0. And I just kind of walked through that together. So now let's start to think about circuits that are a little bit more complicated. For now, we've always been doing things in series. There's only been one path for the current. In the case, the entire circuit has been one single path. But you could have, say, chunks of a circuit that are a single path. So if I have, say, a battery and a resistor, and then some resistors, and then some resistors, and then this wire kind of might think of that as converging or diverging. Based on how I drew the current, seems like currents come in here. 2 different currents possibly come in, and then merge together to go through these 3 resistors. Essentially, you can't have current go through one of these resistors without going through the other resistors. Right? So this one current has to always go through these 3 together. It can't go through this one and skip over the other one. So then we say that these are in series. Essentially, they all come as say a pair, but there's 3 of them. They all come as a group, where an individual charge, as it goes through, once it gets to this junction, can make a choice, and it can go this way or this way. So an individual electron will not go through both of these, because the current is going this way, I claimed, and then this way, and then it goes up. So then they kind of merge here, and I'll go that way. So this is an example of series, resistors in series. The idea of being in parallel is that they are essentially the same delta V across all the paths. So again, if I have a battery, it goes up through the resistor, and then it breaks at this junction, and then it also breaks at this junction. those junctions or those individual paths all have their own resistor, and then essentially everything merges back together to go back into the battery. If you look at the equipotential surface colors, and this is an equipotential surface. Remember, you just essentially just follow the wire until you hit something. So here, you just follow the wires until you hit the resistors. So this is all the same potential, but then this is all the same potential. And notice across this resistor, yellow to red, yellow to red, yellow to red, yellow to red. That's what we mean by parallel. So all those resistors are in parallel. There's the same delta V across all the paths, which makes it pretty straightforward and easy. So let us do an example. I guess I do series again for a little bit, but talk about power. I guess that's fine. Here, I want to actually rederive this for you. A reminder. So before we get to parallel circuit examples like the one at the bottom here, let's consider the power, which I think maybe textbooks should kind of emphasize power from the start, because I think you have a better sense of energy conservation, right? Potential, that stuff gets kind of complicated, even though it really is just potential energy. But you can think of, if I'm drawing 10 watts from the battery, that 10 watts better get used up somewhere. So we can think about, for example, this one at the top. I have a 10-volt battery connected to a 2 ohm, resistor. How bright is the bulb? And what do I mean by bright? Well, of course, I'm talking about how much light is coming off the thing. Which, if I look at a lamp or one of these lights on my ceiling right now, I say that they're bright because they are constantly emitting light, right? So this is a measure of energy, but it's a measure of the energy that's being emitted every second. Right? If the lamp only emitted light for a second, I would say it's dark, because I would see a flash and then nothing. But if I'm talking about energy emitted per second, that is not the laser pointer. Then that's energy per second, of course, is just power. So I think another video derived this, but it's not too hard to sketch out again, because it reminds us of the physics. For a given charge, across the resistor, which that charge is this. Right, those charges are the things that kind of march, they fill their backpacks with energy and they march through the resistor and run into things, which then, dump, I'm mixing up my metaphors here, which then dumps energy into that object. Really, it's their kinetic energy that gets dumped, not little backpacks. But as they go from high to low potential, some of their energy goes into the object itself. And we know from way back when that the change in energy, or the delta change in potential energy for a charge, is Q delta V. That's essentially the definition of delta V. So, and this is for kind of across. Let's take a battery, right? I've been talking about the resistor, but we could also talk about the battery, right? So across kind of battery or resistor, where there's some delta V across the object, be it the battery, right? I gain 10 volts, or across the resistor, I lose some amount of voltage. So delta V is fixed. Right? If I go through the battery, right, that 10 volts is fixed. It's a constant. But then how much energy gets drawn out of the battery is then going to be a function of how many of these little Qs are passing through the delta V every second. So if we think of delta U as the energy kind of drawn or given, so it gets drawn from battery, then we could write, say, that instead of writing delta U, we're going to write E, which is then going to be Q V battery. And then since V battery, again, is fixed, this is just a function of Q. The amount of energy that's being drawn from the battery is the total amount of charge that goes through the battery times that potential difference. So power is essentially the time derivative of E. Right, the amount of energy per time that is going through the battery or across the battery. So then, I know you are all far enough that I can whip out now the chain rule. Power, P, which is defined to be dE by dt. So that's essentially definition. But we just said above that E is a function of Q. So by the chain rule, then that becomes dE by dQ multiplied by dQ by dt. Again, it kind of looks like our physics faux pas, if you think of them as fractions, which again is, the reason why it works is that essentially we're just being a little sloppy with how we say the chain rule. Really, it's just a chain rule. And again, why do I have to do this? Because I said E is a function of Q. Now, if Q is a function of T, then you might say, well, isn't then E a function of T? Well, of course. I could then write E as a function of T if I knew the function for Q. But maybe I don't. I do know, I'm going to get the same exact answer if I think of this as a function of Q. And so then if I take the derivative, not as a function of Q, but of T, but I know Q is a function of T, then that becomes by the chain rule dE by dQ times dQ by dt. If Q is not a function of T, then it would be just 0, where you might be thinking, well, I thought if it's a different variable, it's just 0. But I should have wrote up here, right? E is a function of Q, and then Q is a function of time. How much charge is going through the battery depends on how much time you're measuring, or we can look at the time derivative, which is the power. Now, of course, this thing here, dQ by dt, is current, I. And then if I look at E, the derivative of this thing with respect to Q, since V is just a constant, well, that's easy. Like if I said 3x, what's the derivative? You would just say 3. Here it's V times Q, what's the derivative? You would just say V. So then this becomes V battery times I, which then gives us our formula that the power drawn is the current through the object multiplied by V battery, right? So that's the power, drawn by the battery. And then similarly for resistors, right, P of I R, that's the power. I'm sorry, that's completely wrong. P is IV as well, but this is the V across the resistor, right, which is why I did not write a subscript B. They don't necessarily have to be the same. And then the way for resistors, since V is I times R for resistors, right, don't write this for the battery, but for a resistor, I can substitute in IR, which then becomes I squared times R. So then for resistors, we can write P as I squared times R. I think those deserve a highlight. We got for the battery, and then we got for resistors. So, given that, how bright is this bulb? We go back up to the top. Nope. So this is a pretty simple one. I think you can figure it out on your own without me having to go through all the steps again. But again, I would try just to confirm that you can do it. the current in this case would go clockwise, and I is going to end up being 10 volts divided by 2 ohms, which is again is going to be 5 amps. I don't know why I said again. But then the current in this case is 5 amps. Now, if we want to think of energies, so if we think of them power, which does get used up, because again, this is the amount of energy per second, all right? And there can't be any leftovers, there can't be any deficits. It has to be in balance. So then the battery, I expect the power of the battery to be the current through the battery times the voltage of the battery. Well, there's only one current in this problem, so that's going to be 5. And then the voltage of the battery is 10. So then this looks like it's 50, and the SI unit is watts. So 50 watts are being drawn from the battery. And then how much is getting used up in this resistor? Well, that is going to then be the current through the resistor squared times the resistance, which we said is 5, same current, squared, times the resistance, which is 2. 5 squared is 25 times 2 is again 50 watts. They match, as they should and must. Essentially, the power that gets drawn by the battery goes into the resistor. Then you might be asking, shouldn't one have a negative sign? Well, yeah, but that's for you to, right? You can add the negative signs as you need, right? And I think power is intrinsically always a positive number, but then you can just state, is it power going in or power going out? Here, power is going out of the battery into the resistor. Okay. This power derivation, longer than I budgeted. And this was shorter than I budgeted. All right, now what about this case? Where we have now 2 resistors. And they have different resistances. Now in this case, there's still only one loop. It can only go around in one direction. So again, the battery is going to force current in this direction. I can then draw my loop in this direction, apply the loop rule. And again, you can convince yourself that you're going to get V battery minus I times R1 minus I times R2. Let's call this R1 and this R2. And that's going to then equal 0. Again, because I'm plus V, because I'm going in the direction from negative to positive, down to up, through the battery. And then I'm going in the same direction as the current if I make my loop go clockwise as well. And it's the same current because the current only has one path to go. It does not break apart at all. So notice this is the same thing as if it was VB minus I R1 plus R2 equals 0. So had I said that this was a battery and a single resistor that was 5 ohms, and this is 10 volts, you would have written down the exact same equation. So this circuit here is equivalent to this. So we call this the equivalent resistance, right? I can replace, so then this is the equivalent resistance. Now, what is the one, if I were to replace everything with just a single resistor, what is that resistor? That's the equivalent resistance. And it looks like all we had to do is add them up, which leads to, it turns out, you can try to derive this on your own, that in series, the equivalent resistance is just the sum of the resistors. we'll have sum over little n. Or in this case, there are 2 resistors. There could be 3 resistors, or 10 resistors, or 100 resistors. So as long as they're in series, you can just add them all up. Which notice that this equivalent resistance is always going to be it's always going to be greater than any individual resistor. In this case, it was a 2 resistance, or 2 ohm plus a 3 ohm. And the equivalent resistance was 5 ohms. There's more resistance. And if we think of resistance as resisting the flow of charge, then this is probably going to slow down the current. Now, is that 2 ohm bulb, notice both these have a 2 ohm bulb, is this bulb going to be just as bright as this one? So it's up to the same battery, but what does the presence of this other light do? The fact that it's in series. Well, when we solve this, this implies then that the current is going to be VB divided by 5 ohms instead. So we already can see that it's different. Because now we have 10 divided by 5, or 2 amps. Where before we got 5 amps. So the current has, we can already see that the current has dropped. There's less current flowing. And again, not because it's getting used up in any way, but there's a more resistance, right? Essentially the path that the current has to travel encounters more resistance, which makes it overall travel slower. But still, little electrons with their little packets of energy filled with 10 volts. But in this case, some of them dump their energy to one of the bulbs, and the rest of them dump it to the other bulb, such that collectively they use up 10 volts. Right, notice again with this loop rule, right? I gain my 10 volts, but then I lose all of it through the resistors. It's not that, you know, all of the electrons could dump it all into the first bulb and then there's nothing left for the second bulb. Yeah, here's where this kind of anthropomorphizing, you know, the charges kind of breaks down, because then, well, how do they decide which bulb they're going to dump their energy into? Well, they're also not making these decisions consciously. So as a result, essentially the resistance, you know, determines kind of what fraction gets dumped into which bulb. But we can, again, look at the power. So the power of the battery is the charge current through the battery times the voltage of the battery. So then that's going to be 2 amps times 10 volts, or 20 watts. Notice it's different. We had 50 before, now only 20 watts. You put another bulb in, which you might think means we need to do more, because now I have 2 light bulbs to light up. But I put a second bulb in, and I ultimately draw less overall power. So then the power of resistor 1, which is going to be the current through resistor 1, times the resistance, or resistance 1, sorry, the current squared. So then it looks like it's going to be 2 squared times, and then it was a 2 ohm. So 2 times 2 is 4, times 2 is 8. So we got 8 watts going through that first bulb. Before we had 50. Now we only have 8. Then what about that second bulb? Well, it's going to be the current going through that bulb times its resistance. So you're going to have 2 amps squared, and its resistance was 3. So we got 2 times 2 is 4, times 3 is 12 watts. And then, what is 8 plus 12? Total, that is 20 watts, which matches the battery. So again, what conceptually do we take away? When you're adding these things in series, the resistance ultimately increases. We said that here. But by increasing the resistance, you decrease the current. The path of least resistance has now not become quite as least resistant. So you decrease the current overall, which ultimately means less power is drawn. Which, well, I guess you're too young. Or maybe if your parents or grandparents had like really old Christmas lights. Those Christmas lights were typically drawn in series. So, well, in that case, if one of the bulbs broke or went out, the entire circuit was broken and the entire strand stopped lighting up because the circuit was broke. But essentially, if you could also compare like strings that have 10 lights versus 20 lights versus 50 lights, and essentially they would get dimmer and dimmer as you had more attached. Let's see if that's the case now for this parallel example, where we'll take, again, the 2 and the 3, but now notice I have them connected in parallel because if I draw my equipotential surfaces, it's yellow to blue across this one, and it's also yellow to blue across this one. So they are connected in parallel. Because of this junction, it then seems like the charge has to make a choice. When an electron gets to this intersection, it has to decide whether it's going to go down or whether it's going to keep going straight. So I can imagine that the current must divide as a result. So I expect the current to divide or do something at the junction. By saying divide, I'm actually kind of saying what the answer is, where, of course, charge conservation is going to be obeyed. But even if we didn't know that, we could still figure it out and conclude that ourselves. So we can at least say that, well, there's going to be some I battery that goes through the battery, whatever it is. Then there's going to be some current, we'll call it I1, that goes through this resistor. And this some current I2 that goes through that resistor. And I'm going to make educated guesses that it goes up and then the other two go down. So then it kind of goes that way, and then it goes that way. At least through the resistors in the battery, it seems like there's possibly 3 different values of the current. Now, so again, I've guessed the direction of the current. And then, in this case, I still just look for loops. So there's a loop that kind of goes through the battery, and then goes down the first resistor. That's a loop. So if I wanted to, I could write out Kirchhoff's law for that. So for that loop, I'm going up through the battery, so I get V battery, and I'm going down through the resistor in the same direction as the current. So it looks like that's going to be I1, R1, and then I'm back to where I started. Again, no matter what loop I make, I can't have any leftover energy. And then, I could ask myself, what do I know and what do I not know? I know V battery, that's given, 10 volts. I know this resistance. I can now solve for this current. That's convenient. There's only one unknown in this equation. So then I get I1 is V battery divided by R1. So you got 10 divided by 2, or 5 amps. And we're back to 5 amps. There's 2 bulbs in the circuit, but now the current seems to go, is its original value. It did not decrease like the series one did. But I still don't know the other 2. Well, I could try to find another loop. Another loop might be I go up through the battery, and then down through the other resistor, and then go back. And I'll have the loop go in the same direction as the current again. And then it looks like in that case, I'm going to get up through the battery, down through the resistor, that's I2, and R2 equals 0. So then, convenient. And it looks like I2 is going to be V battery R2, 10 divided by 3, or 3.33 amps. And now we still have the current that's going through the battery that we don't quite know yet. Now, it turns out that we can choose charge conservation, or we could maybe try to conclude that on our own because of energy conservation. So the power through resistor 1, which is I1 squared times R1, if I do that calculation, that's going to be 5 squared, which is 25, times 2, so that's 50 watts. And the power of resistor 2, which is going to be the current through it, now it's different, I2 squared, R2. So that's 3.33 squared, then multiplied by 3. So that's, let's see how many decimal spots we need to keep track of. Yeah, well, let's do one decimal spot. So that ends up being 33.3 watts. And so in total, it seems like 5, 6, 7, 8, 83.3 watts are kind of in the bulbs. So then I could say by energy conservation, the power of the battery better be the current that goes through the battery times the potential of the battery. The potential of the battery is 10, so it seems like we need 10 times the current through the battery. That better equal 83.3 watts. That is only the case if the current through the battery is 8.33. Should have kept another decimal spot around, but trust me, there's more threes. Not watts, current is not energy, amps. And then you can note that what's a way I can get 8.33? Well, it turns out that that is just I1 plus I2, which was 5 plus 3.33. So in this case, we have figured out the currents everywhere in the circuit, and the problem is solved. Then I can compute powers if I want and stuff like that. So conceptually, what do we notice? This first bulb is just as bright as if it was just by itself. Essentially here we had the bulb by itself and it had 50 watts. Here the bulb is kind of by itself on this path and it drew 50 watts. But then this bulb also drew some energy. And so overall, where in the case of the series, they kind of worked against each other and they kind of damped down the current. Here it seems like they made the battery work even harder because they each wanted their own, essentially ignoring the other one, right? I never had to factor in the other resistor when computing these two currents. But then as a result, in total, the current drawn through the battery was much higher. Here was only 5 amps. Here it became 8.3, 8 1/3. Which is kind of a general result of series and parallel. Series slows everything down. Parallel, at least through the battery, can really speed things up. And then notice that the current through this first resistor was 5. The current through the second resistor was lower, it was only 3.3. But then notice the second resistor had a larger resistance. So the path of least resistance is also the path that more current flowed down. The path with more resistance ended up having less current overall. Again, trying to motivate why we call it resistance. Now again, this idea of that charge, the currents are really just the sum, is really just a statement of charge conservation. What's going on is that at this junction, the charge had to make a choice. Each charge could either go right or down. So essentially, what came in had to be balanced by what went out. Pretty simple. So that's the second law for Kirchhoff's rules. That at a junction, the currents that go into that junction better be balanced by the currents that go out of that junction. Kind of like what I just described, so I won't bother kind of redrawing it. Well, let's redraw it. Right, at this junction, I know that current could separate. So in this case, there's going to be some current that goes through the battery, but then it can break off and either go down, I'll call that I1, or go to the right, I'll call that I2. But then when it gets back to this junction at the bottom, so notice that then essentially what this junction is saying is that I battery equals I1 plus I2. But then here at junction 2, I1 plus I2 come in, and then I battery better come out as a result. So what this does is this gives us another way of writing down an equation, because now we're going to have multiple currents. In this case, we had 3 currents. So if you go back to the example where we worked it out, we had 3 unknowns. We had I battery, I1, and I2. If you have 3 unknowns, that means you need 3 equations. 3 equations for 3 unknowns. And notice we had equation 1 here, equation 1 here, equation 2, and then equation 3. Essentially is a way to think about this. We did power, which of course is another way of doing it. So I could say that my kind of procedurals now just has a little upgrade, but it's more or less exactly the same. So given a circuit, guess the direction for I everywhere. You might, and in this case now you also have to determine how many currents there are. In this case there might be as many as 3 currents. And then I guessed we could guess a direction for all of them. And again, as long as you're consistent and there's no absurd contradiction, like I battery comes in and I1 and I2 come out here, but then down here you say that I1 and I battery come in, but then I2 come out, right? That can't happen. As long as you're consistent, even if you put them in the wrong direction, you'll just get negative signs. And then you still draw any loop you want. Doesn't even have to go through the battery. I could have did this loop. That was another loop we could have done. Where I could start here and kind of go up, and that's a loop, even though it doesn't involve a battery. To apply the loop rule, and then essentially you just repeat this step, maybe plus the junction rule, as many times as you need until you have enough equations. In this case, there were 3 unknowns. I had 2 loops, and then 1 junction rule that gave me my 3 equations. So let's see. I left all the space. I think I intended to actually write all that out, but I don't want to. So I guess there's one thing I'll point out. One thing I'll point out is that sometimes a given loop won't tell you anything new. So sometimes, you might say, let me redraw it. I'll just do this qualitatively. So we had the battery, with the resistor, we had another resistor. So V battery, then we have R1, R2. You could have said, well, screw the junction rule. I'm just going to draw 3 loops. You can say, okay, there's 1 loop here. I can do that. That's 1 loop. I can do the second loop here. That's the second loop. So that's going to be a second equation. And I have this one here. That's the 3rd loop. But it turns out that that doesn't give you enough unique information. I can just sketch out why. When I do the blue loop, we got VB minus, so bold. We got VB minus I1 times R1 equals 0. Then we did the red loop, we got VB minus I2 R2 equals 0. Then we did the green loop. And you remember, we think the currents are going down through both. And let's do a clockwise green loop. So clockwise green loop means I go up through R1 and then down through R2. So it looks like it's going to be then plus I1 R1 minus I2 R2 equals 0. Notice there's no kind of IB or I battery anywhere. This blue one essentially gets you I1. This one gets you I2. I can solve them and get the numbers. But then I know I1 and I2, so this doesn't tell me anything new. I can't get a contradiction. When I plug I1 and I2 into that third equation, it better equal 0. And it does. But notice it doesn't help me figure out what IB is. So in that case, I need some third equation that brings in the third unknown, which then is just the junction rule. And of course, the powers all adding up do have to work too, which I believe I said here, correct? Yeah, essentially, in this case, what does have to all add up because it gets used up? The energies. So the sum of the two powers through the resistors did add up to be the power of the battery. Okay. Do I want to do equivalent resistance? Well, we kind of do. I don't think I'll do the more complicated example on the back, though. Or maybe I'll just jump to the answer here. I'll talk through it fast, because you can just read the book. So, we can also talk about equivalent resistance for things in parallel. So the way I sometimes think about it is, imagine you had a box you bought, and there was a claim that there's a single resistor in that box. And when you hook it up to the circuit, then you have a battery, and it goes through a single resistor and goes back. That's a very simple circuit that you can draw, right? And you would write down that VB minus the current through the battery times this, whatever this resistance is, better equal 0. All right, that's a simple circuit. But then you open the box and realize that it's not a single circuit or a single resistor, but it's actually a bunch of these resistors in parallel. There's n of them, and they each might even have different resistances. So this has to somehow be the same as this. So essentially then we can try to write down an equation where we can then equate this to some combination of these. And it's not too hard. Essentially, the junction rule says that I through the battery is then going to be, if you imagine there's going to be I1 through R1, I2 through R2, I capital N through R sub n, where I battery is going to kind of launch out the top. It's going to fraction off down the resistors, and they're going to all, at all these junctions. And then it's going to just combine back up. And eventually, when it gets here, it's back to being I battery. So then I battery is going to be I1 plus I2 plus ... plus I capital N. That's just the junction rule. And then if you do a simple loop, right, I could go through this battery and then down this resistor. That's a loop. Or I could do through the battery through this resistor. That's a loop. You can imagine there's a loop for every resistor where I go kind of through the battery and then down the particular resistor, little n, where n is either 1, 2, ... all the way up to capital N. So, for example, I1 is VB divided by R1. I2 is VB divided by R2, etc. So then just add them all up. The sum of all the currents I1 plus I2 plus I3, etc., is then going to be VB over R1 plus VB over R2, all the way up to VB over R capital N. Or, notice that there's the same V everywhere, so let me factor that out. It looks like it's 1 over R1 plus 1 over R2 plus 1 over R sub capital N. And that ultimately we said is equal to I battery, because it was the sum of all the currents. But then I battery, if I go up to the very top, I said that I battery is connected by this expression. Or it looks like I battery is just VB divided by R equivalent. So then the V's cancel, and I get that 1 divided by the equivalent resistance is equal to the sum of 1 over the R sub little n's, and I just add them all up. Now, admittedly, this looks a little bit more complicated than the series one. This is for parallel. So if the resistors are in series, you just add them together. If the resistors are in parallel, then you are adding them together, but in a different way. It's 1 over the equivalent resistance is kind of the sum of 1 over the individual resistances. So the pitfall you have to remember is that you're solving for R sub E, this equivalent resistance. So if you just do this part and stop, well, then you're not going to get the right answer, because then you have to, what you got there is 1 over R. Then you have to invert it. So let's do this an example real quick. It's pretty easy to see that this is parallel if I draw my equipotential surfaces. So I have my kind of parallel section here. I'm going to figure out the equivalent resistance so I can replace them with just a single resistor. Because if it's a single resistor, my life gets a lot easier. So then, to do that, I go 1 over R equivalent is equal to, looks like 1 over 2 ohms plus 1 over 4 ohms. So I could find a common denominator, multiply the first one on the top and bottom by 2, and this becomes 3 over 2 ohms, or it's the same thing as 3 halves multiplied by ohms to the negative 1. Right, and again, notice the units are not correct. It's not ohms, it's 1 over ohms. And that's because this expression is 1 over the equivalent resistance. So then R equivalent ends up being 2/3 of an ohm. So then that means that this circuit is the same as if there's just a single resistor with 2/3 of an ohm as the resistance. And this is still 9. Now, what does this allow you to solve for? Because it seems like I've completely changed the circuit. Before there were kind of 2 paths for current to take. Now there's clearly only 1. So is this science fiction, or do I still learn something? What's the same between kind of the original and the simplified one? That's what's going on with the battery. I took the right half of this thing and replaced it with this new right half. But the left halves are the same. So in this case, if I battery is going through that, then of course here, I battery better still be going through the battery. But now since I've simplified it, I know then that I battery is going through this hypothetical equivalent resistor. So I can write V battery minus I battery times kind of R equivalent equals 0. Or that I battery equals V battery over R equivalent, which are the numbers the same as what I had up here? I feel like I've gone from, oh, these were 9. Okay, never mind. So what did we get before? We got that the current was 8.33 amps. And then here we said that V was 10 and R equivalent was 2/3. Lo and behold, that is 8.33 amps. No, it is not. Let's see. Well, first V was 9, not 10. But that does not fix things, so I've gone too quickly and I've made a mistake somewhere. Let's see, where did I make a mistake? Or am I comparing apples to oranges here? Because I changed some of these 9s to 10s, and oh, I did. I changed this to a 10. So that makes this different. So the equivalent resistances are the same. Let's make this 9 a 10. Let's make this 9 a 10. So then, when we do that, that makes the problem worse. Oh dear, what have I done wrong? Yes. I was about to ask, does anyone see? But not that you can reply. Oh. I need to go back and learn how to add fractions. So let's do this part again. So R equivalent, the formula, is 1 over 2 ohms plus 1 over 4 ohms. Then I could multiply this by 2 and this by 2. So then that becomes 3 over 4 ohms. And again, that's the same thing as 3/4 ohms to the -1, because that's 1 over the equivalent resistance. So then the equivalent resistance is 4/3 ohms. So then I do 10 divided by 4/3, then I get 8.33 amps. I'm going to claim I meant to do that on purpose. Why? Because it gave us an opportunity to actually sit and think about the numbers we were getting, rather than just getting a number and blindly moving forward. You'd always ask yourself if things are making sense. And the fact that I had 10 divided by a number less than 1, that was going to be impossible for, I can't divide by something by less than 1 and have the number go down. So 10 divided by 2/3, I knew had to be greater than 10, so I knew something was up. So you're welcome. So, things that we've noticed. I think I'll leave it here and leave this example for class. When things are hooked up in series, that slows things down, because essentially the equivalent resistance is just the sum of the resistors. The path of resistance then becomes more resistant, and the current decreases. In parallel, however, essentially each path acts independent of each other, and so they each draw whatever they want to draw from the battery. This essentially is an extension cord, but you can imagine, just think about this one at the bottom. I'll sketch it out real quick here in the bottom. If I have a battery, then I have an extension cord that I've filled up with various things. Each of them is drawing, say they're all the same resistance. If each of them is drawing 5 amps, 5 amps, 5 amps, 5 amps, 5 amps, then suddenly this battery has to be chugging out 25 amps. What kind of battery is if it could even do that? So in this case, why is this dangerous? Because notice how here the current could be arbitrarily large if I just keep hooking things up in parallel. I just keep adding in maybe I hook up another extension cord to one of the outlets of my extension cord. Why is that an absolutely terrible idea? Essentially, you're just then adding more things in parallel. And you might get, again, if they're all equivalent, if they're each the same resistance, right, then they're each going to draw 5 amps. And things get, and then suddenly the power that's going through the battery is some giant current times 10 volts or 9 volts or whatever it is. That can be a lot of power. Things heat up, things might start to spark. So in this case, and I won't do this one, I'll do, maybe try this out. Maybe I'll have you sketch parts of it at the start of class. Essentially, if all the bulbs are 1 ohm resistors, determine the power that goes through each of them. Now the tactic here, I won't solve it, but I'll give the tactic, is let's identify our equipotential surfaces. Looks like there's going to be the low one there. And there's going to be, looks like that one there. I could take this more complicated circuit and try to make it into a single resistor. Because then I can easily get the voltage of the battery, I can easily get the current through the battery. But to do that, I need to use the 2 formulas. I need that R equivalent is the sum of the R's when it's a series, or that 1 over R equivalent is the sum of 1 over the R's in parallel. So, what do we notice? Let's see, let me use a different color. Notice that these two here are in series. The entire circuit's not series, but those two are in series. And then blue to green, like these two are in parallel. So I could, in series, I just add them together. So if they're each 1 ohm, the equivalent resistance is then a 2 ohm resistor. And in this case, they're each 1 ohm. Turns out the equivalent resistance is going to be end up being 1/2 of an ohm. Let me work that out. So then I could take this more complicated circuit and replace it with something that's a little bit simpler, where I have now a 2 ohm resistor here, the replacement. Then it goes out. And then I've replaced this entire parallel thing now with a single 1/2 ohm resistor. Then there's still that one on the bottom. That's still 1 ohm. We didn't do anything with that with bulb number 5. And then it goes back to the battery. Now we could do it again. There's a equipotential surface. There's one. There's another one. What do we notice? Notice these two are in series. So that's nice. I can just add them together. So then this becomes, I still have that 2 ohm one. Didn't do anything there. But then I replace the other two with their equivalent, 1 plus 1/2. So that's 3/2. So notice I've made the circuit even simpler. And then I look at my equipotential surfaces and notice blue to yellow, that is parallel. And so as a result, you could figure out the equivalent resistance of them, and I believe you get 6/7 of an ohm in that case, which then ultimately allows you to draw this entire circuit, that complicated thing we had originally. We've turned it into one battery, one resistor that has a particular resistance. Notice none of the individual bulbs have this resistance, right? They're all 1. But when I take this entire circuit and turn it into one equivalent resistor, that's the equivalent resistance. And then that's a hella simple loop that I can do. That gives me Well, it turns out it looks like I'm solving this problem, but I'm not going to solve it after this. So then that loop says that V battery minus I battery times 677 ohm better equals 0. So that gives me I battery. So in this case, I battery ends up being, I believe, 10.5 amps. And now the task is that, okay, I figured out I battery. But I still need to figure out all the other currents. If I go back to, I have some, oh, there they were. Did iOS update, and now this app seems super sluggish. So if I go back to the original, the current, right, makes sense that there's some current through the battery. Call that I battery. And then there's a junction here, so there's going to be some current that goes down here. We'll call it I1. And there's some current that goes out here. Let's call it I2. But then I2 hits another junction. So then, well, that's unfortunate. I should call this I2. Let's call this I, dear. Let's call this I mid. And I mid divides so that then you have I2 going down that path, and then I3 going down that path. I2 and I3 merge back together to go through this one, which we called I mid. And then those two merge back together and become V battery, or I battery again. So the junction rule, just to write one of them down for good measure, essentially I battery equals I1 plus I mid. That's what this is saying. And then here, it looks like I'm saying that I mid equals I2 plus I3. And the other junctions are just, are not going to tell us anything new, because the one at the bottom here is going to be the same formula. And then the one here is going to be the same formula as one above it. So maybe that helps us, because that gives us two equations. So to think about what are all our unknowns, it looks like we have I battery, we have I1, we have I2, we have I3, and you might say we have I mid, but I mid is just a combination of these. And essentially the junction rules help us out, right? So essentially the kind of equivalent, the equivalent resistance trick we just did gave us IB. And then we could use, IB equals I1 plus I mid. Well, I know IB, but then that's only one equation with two unknowns. And then I have kind of I mid equals I2 plus I3 from the junction rule. Again, I know IB, but that doesn't help us, right? That's kind of two equations. Well, it will help us, right? That's two equations, but there's essentially three unknowns. Because I could substitute, I could get rid of I mid and get kind of one equation with I1, I2, and I3. So I need more equations. Essentially, since there were 5 things here, I need 5 equations total.